A construction crew just finished installing what looked like ordinary architectural glass on the south face of a government pilot building. It wasn't ordinary. Every panel was generating electricity. The building's grid draw fell 40% compared to an identical structure next door. Not because of rooftop solar, not because of some bolted-on generation system, but because of the windows themselves. That number matters because it beats the roadmap. The International Energy Agency's own projections didn't expect building-integrated photovoltaics to hit this kind of performance until 2030. The engineers W. Ho first saw the data, didn't believe it either. They demanded a second independent verification before anyone was allowed to publish it. Think about what that means. This isn't a demo unit in a lab, wired up under perfect lighting with a research team standing by to catch anomalies. This is a working government building, exposed to real weather, real dust, real seasonal sun angles, real occupants running the HVAC and the elevators and the lights the way people actually do. And it's still outperforming a decade-old technology roadmap by 4 years on a metric the solar industry spent 30 years failing to approach. Here's the truth behind that number, and it requires tearing down a few things you probably assume about solar power. For 50 years, glass had exactly one job in a building. Let light in, keep weather out. That was the whole job description. Solar cells, meanwhile, worked by doing the opposite, absorbing photons, converting them to current, and going dark in the process. Combine the two, and you don't get an engineering challenge. You get a contradiction. A transparent power-generating window sounded less like a hard problem and more like a wrong one. The physics backed that up. Capture more photons, generate more power. Capture more photons, the material gets darker. You could build a solar cell, or you could build a window. Nobody had built both at meaningful efficiency, and the world's best labs, NREL in Colorado, Fraunhofer ISE in Freiburg, MIT's Energy Initiative, had spent 2 decades proving why not. By the late 2000s, the ceiling was locked in. Semi-transparent photovoltaic glass topped out around 8% power conversion efficiency. A standard rooftop silicon panel was already hitting 22%. The gap wasn't a mystery waiting to be solved. It was treated as a structural feature of the technology. Money made the wall taller. Building integrated PV glass cost $400, $900 per square meter installed, against $80, $120 for ordinary curtain wall glass. At 8% efficiency and a 4 to 8x price premium, payback stretched to 25-40 years. Commercial leases run 10. No developer with a working spreadsheet was going near it. The ceiling had a number, a price tag, and a decade of consensus behind it. The industry had stopped trying to break it. Architects designing curtain wall systems, the continuous glass skins that define the skyline of every major city, optimized for exactly 3 things: visible light transmittance, thermal performance, and structural load. Bolting on an expensive, underperforming solar function that compromised all 3 wasn't a serious conversation in most design offices. It was the kind of idea that got a polite nod in a meeting and never made it into the construction documents. The ceiling wasn't just technical, it was cultural. An entire generation of engineers had been trained to treat solar glass as a compromise product, not a real one. What changed wasn't a lab result. It was a spec sheet, no keynote, no press conference. Just a product specification from Longy Green Energy, already the world's largest silicon solar module manufacturer, claiming over 12% power conversion efficiency on commercially produced semi-transparent PV glass paired with visible light transmittance that met standard architectural glazing codes. Not a lab demo, a shippable product. The research world's response was fast and skeptical. Fraunhofer flagged that efficiency claims for semi-transparent systems are wildly sensitive to test conditions. The IEA's Photovoltaic Power Systems program marked the number unverified against IEC standards. Trade press called it aspirational. The specific objection, depositing a functional tandem cell onto float glass at production line speed, while holding both optical clarity and electrical uniformity, had never been demonstrated at scale. The claim implied a manufacturing process that, as far as anyone outside the company could tell, didn't exist. People said something similar about Chinese lithium iron phosphate battery claims in 2020. The global battery industry now runs on that chemistry. People said something similar about Chinese dominance in EV battery CALL production before it happened, and about solar wafer manufacturing before that too. There's a pattern here worth naming plainly. Western research institutions are very good at defining the physical ceiling of a technology and consistently slow to recognize when an industrial operator has quietly built the manufacturing capability to punch through it. The 2 things get evaluated by different disciplines, on different timelines, using different evidence, and the gap between them is exactly where announcements like this one land, sounding impossible right up until someone ships the product. What the skeptics missed was what the spec sheet actually represented. Not a prototype boast, but the output of a vertically integrated operation that had been quietly running for the better part of a decade. LONGi hadn't started with the glass, they'd started with the cell. Their heterojunction silicon technology had already pushed single E-cell efficiency past 26% in lab conditions, a world record. The BIPV glass line was that cell chemistry applied to a new substrate by a company that already controlled the float glass supply chain, the deposition equipment, and a domestic construction market big enough to absorb the cost of learning a hard new process at scale. No Western competitor had assembled that combination. This wasn't a lab boast, it was a manufacturing declaration. That distinction is the whole story, and it's worth sitting with. A research paper announces what's possible, a specification sheet announces what's already running on a line, ready to ship in volume, priced, tested, and repeatable. LONGi wasn't asking anyone to believe in a breakthrough. They were telling the market what came off their factory floor last quarter. Those are different categories of claim, and treating this M the same way, as the trade press initially did, is how an entire industry gets caught flat-footed. The real obstacle in BIPV glass was never chemistry. It was speed. A float glass line never stops. Molten glass spreads across liquid tin, flows through a temperature-controlled annealing chamber, and moves continuously at meters per minute. The entire process exists to produce. See optically flawless glass as cheaply as possible. Stop the line, or slow it to apply a solar cell layer using conventional batch sputtering, and you kill the cost advantage that makes float glass the default building material on the planet. The old workaround treated glass and cell as separate jobs. Make the glass, cut it, ship it to another facility, coat it in a controlled batch process, ship it back. Every handoff added cost, breakage risk, and time. The result worked technically and lost commercially. LONGi's engineers built something different, an atmospheric pressure chemical vapor deposition system running in line with the float glass process itself. Picture it less like painting a wall one panel at a time and more like running glass through a Preggy-Cyan fog chamber at the exact speed it's already moving. Chemical precursors enter as controlled vapor at specific temperature zones along the existing line. He glass never stops. The cell chemistry bonds uniformly because the deposition environment moves at the same speed as the glass passing through it. At LONGi's pilot facility, that inline process held 13.1% power conversion efficiency under IEC 61853 standard conditions across a full production run, not a cherry-picked KED sample. Optical consistency met architectural glazing codes for commercial curtain wall. This isn't a coating applied to a window. It's a window grown around a power cell. Deposition was solved, and it's worth pausing on how unglamorous that solution actually is. There's no exotic new material here, no breakthrough particle physics. It's process engineering, the unsexy discipline of making an existing chemistry run at the speed and uniformity that turns a lab curiosity into a shippable product. That's precisely the kind of problem outside observers tend to underrate, because it doesn't produce a headline-friendly discovery. It produces a factory that quietly works when everyone assumed it couldn't. But the fix created a new problem, and it lived right in the part of the spectrum human eyes actually use. The tandem cell architecture that made inline deposition work absorbed light broadly by design. A perovskite top layer catching high-energy photons, a heterojunction silicon bottom layer catching the rest. 2 layers, sequential extraction, maximum current. The problem, the visible spectrum, 380 to 700 nanometers, the band human vision runs on, sat right inside the perovskite layer's absorption range. The glass coming off the line was tinted, not opaque, but enough. Visible light transmittance on early samples measured 28%, which failed daylighting codes in most major markets and failed the far simpler test of whether people working near it felt okay about it. The trade-off was brutal and clean. The more efficiently the cell absorbed light, the darker the glass got. The more transparent the glass, the less power it made. Every industry player had picked a point on that curve and lived with it. Nobody had escaped it. LONGi's materials team didn't try to escape the curve. They changed what the cell was being asked to absorb. The fix was a luminescent solar concentrator layer, a thin film sandwiched between the glass panes, built from cadmium-free zinc copper indium selenide quantum dots, tuned to absorb near-infrared and ultraviolet light, specifically the parts of sunlight human eyes never register. Instead of competing with visible light for the same photons, this layer intercepted the invisible bands, re-emitted, them at wavelengths matched to the cell's peak absorption, and funneled them to the cell through internal reflection. Visible light passed through mostly untouched. TÜV Rhineland's Shanghai facility certified the combined system, inline tandem cell plus concentrator layer, at 14.2% power conversion efficiency, alongside 43% visible light transmittance. Both numbers, same panel, same certification, under IEC standard conditions. It sounds impossible because it asks 2 layers to do 2 different jobs on the same piece of glass at once. That's exactly why it works. The cells stopped competing with the window. They split the light between them. It's worth being precise about why this is clever rather than just complicated. Every prior attempt to close the transparency efficiency gap tried to negotiate a better trade-off on the same axis. Shave a little. Darkness off. Accept a little less power. Inch along the same curve everyone else was stuck on. The quantum dot layer doesn't negotiate on that axis at all. It moves the entire problem to a different part of the spectrum, where there's no negotiation needed, because nobody's eyes are using that light anyway. That's not an incremental improvement. That's reframing the constraint until it stops being a constraint. A single certified panel is a materials result. A 40-story tower with 12,000 square meters of glazing, every panel producing a different output depending on orientation, shading, sun angle, temperature, and the exact spectral mix hitting it that second. That's a network problem. And network problems at that scale don't solve themselves. Standard building energy management systems weren't built for this. They were designed around fixed demand, lighting, HVAC, elevators, pulling from a stable one-directional grid. Wire in 12,000 variable. Microgenerators in that model doesn't bend, it breaks. A south-facing panel in direct noon sun can be producing peak output, while a panel 2 meters away, half-shaded, produces almost nothing. The fix deployed in China's zero-carbon building pilot program, a priority track under the 14th five-year plan, put a distributed microinverter behind every single panel. Each one performs real-time maximum power point tracking, converting variable DC into stable AC, regardless of what its neighbors are doing. Those microinverters feed a building-level AI layer that functions like a traffic control system for electrons, reading panel output second by second, cross-referencing it against real-time HVAC, lighting and elevator demand, and routing generation to the highest priority load first, with grid export as the overflow valve. At the Xiong'an area government complex, the program's flagship site, 8,400 square meters of BIPV facade glass went up across 3 connected buildings. Annual metered output, 1.26 million kilowatt hours. Total building demand, 2.9 million. The glass alone covered 43% of the load from surfaces that, in any conventional building, contribute nothing beyond keeping the rain out. This isn't solar panels on a building. This is a building that's also a power plant. And the part that's easy to skip past, none of this required a new kind of building. Xiong'an's towers look from the street like ordinary glass office buildings. Nobody walking past sees an energy installation. The generation is invisible in the most literal sense, built into a surface that was always going to be there anyway, doing a job it was never asked to do before. That's a fundamentally different deployment model than rooftop solar, which requires available roof area, structural reinforcement, and usually a visible retrofit. Facade glass is going up regardless. The only question was whether it stayed dumb or got put to work. The result was big enough that the program's oversight committee ordered an independent re-verification before releasing it. The China Building Material Test and Certification Group, operating under CNAS accreditation, checked the Xiong'an site's metered output against installed facade area and confirmed a normalized generation figure, 148 kilowatt hours per square meter per year, under real operating conditions. Not lab simulations, not standard test conditions, but a full annual cycle of actual weather. Scale that to a fully glazed 40-story tower with 15,000 square meters of active facade, and you're looking at roughly 2.2 million kilowatt hours a year. The average Chinese urban household uses about 1,800 kilowatt hours annually. One building's glass skin, generating power as a side effect of keeping the weather out, could cover the annual electricity use of more than 1,200 homes. Measured against the IEA's 2023 grid emissions benchmark for Eastern China, that's 1,040 tons of avoided CO2 per building per year. None of this is free, and none of it is being spun as free. The full system, panel, microinverter, AI management layer, costs 45-60% more than conventional high-performance curtain wall glazing at equivalent spec. At today's commercial electricity prices, simple payback runs 14 to 18 years for a standard commercial building. The perovskite top layer degrades faster than conventional silicon, roughly 0.6% per year under accelerated weathering, versus 0.3 and 0.5% for standard crystalline silicon. And the building codes that would let BIPV glass count as a primary energy system, rather than an ancillary add-on, don't exist yet in the EU, the US, or most of Southeast Asia. These aren't footnotes. They're the live constraints on deployment everywhere outside China's own construction pipeline. And yet the number stands, independently certified, installed, metered across a full year on a functioning commercial site. A result the IEA's own BIPV roadmap didn't expect for commercial products until the end of this decade. None of the trade-offs listed above are being hidden or spun by the people who ran this pilot, which is itself notable. A technology this new, with numbers this favorable, would be easy to oversell. Instead, the degradation rate, the cost premium, and the missing regulatory framework are sitting right there in the same disclosure as the headline efficiency figure. That's usually a good sign that the underlying result is real. The people closest to the data aren't afraid of the parts that complicate the story. Buildings account for 37% of global energy-related CO2 emissions. More than transportation, more than heavy industry. That's the standing stock of every heated, cooled, lit, ventilated structure on Earth, most of it designed before climate targets existed. The building envelope, roof, facade, glazing, is the single largest untapped surface for distributed power generation anywhere in the built environment. Every serious net zero building standard, from the EU's Nearly Zero Energy Directive to Singapore's Green Mark Platinum framework, has already flagged it as the next mandatory frontier. The regions watching hardest aren't necessarily the obvious ones. The Middle East, Riyadh, Dubai, Doha, is building glass-dominant high-rises faster than anywhere else on Earth, has the solar resource to match, and has national energy transition mandates that make BIPV glass compelling if the cost curve keeps bending the right way. Southeast Asia has a similar profile: rapid urbanization, strong solar resource, and a construction pipeline outrunning its own grid capacity. Inside the EU, the revised Energy Performance of Buildings Directive requires all new commercial buildings to be solar ready starting in 2030, a regulatory demand signal with no adequate domestic supply chain behind it yet. The patents aren't the bottleneck. Patents are available. What adoption actually requires is the full stack: float glass manufacturing capacity, inline cell deposition, quantum dot layer chemistry at production volume, microinverter supply chains, and an AI management layer mature enough to handle real-world variability. China spent roughly a decade assembling all 5 inside a domestic market large enough to absorb the learning, size, curve, cost of each piece. No other country currently runs all 5 at commercial scale simultaneously. The EU's own BIPV action plan acknowledges the gap directly and doesn't point to a funded domestic program closing it. There's precedent for how fast this can flip. In 2005, Japan's Sharp and Germany's Q-Cells led global solar module manufacturing. Chinese producers held under 5% of world output. By 2023, that number had passed 80%. The module transition took 12 years start to finish. The BIPV glass transition is running roughly 15 years behind that curve, which, if the pattern holds, means it isn't a question of if, but of how many years. It's worth noting what that transition actually looked like while it was happening, because it rarely looked inevitable in the moment. In 2005, most Western analysts treated Chinese solar manufacturing as a low-cost assembly, operation riding on subsidized capital, not a serious long-term threat to German and Japanese technology leadership. The consensus view was that the West held the IP and the process knowledge that actually mattered, and that cost advantages alone couldn't close a technology gap. That consensus was wrong, repeatedly, for over a decade, right up until it wasn't. The same confident dismissal is visible again in the early trade press reaction to the Longai BIPV announcement. Recognizing the pattern doesn't guarantee this transition follows the same path, but it should at least raise the burden of proof for anyone confidently predicting it won't. The transparency-efficiency trade-off wasn't a permanent law of physics. It was a manufacturing integration problem dressed up as one. And manufacturing integration problems don't get solved in a lab. They get solved by a company that has the cell chemistry, the production infrastructure, and a home market large enough to absorb the cost of working it out commercially. China had all 3 at once. Nobody else currently does. The inline deposition process made the cell viable at production speed. The luminescent concentrator layer split the spectrum so the window and the cell stopped fighting over the same photons. The microinverter network and AI management layer turned 12,000 unpredictable panels into one coordinated system. And the independently certified result, 148 kilowatt hours per square meter per year, measured on a real building through a real year of weather, proved it works outside a lab. The physics stopped being the limit years ago. The industrial system built around the physics is what's catching up now. That reframing has consequences beyond one manufacturer or one country. For 30 years, the conventional wisdom in energy policy circles was that breakthroughs in generation technology come from research budgets, fund the labs, fund the universities, fund the national initiatives, and eventually a discovery emerges that changes the cost curve. That model produced real results. It's also, on its own, an incomplete model. What actually turned an 8% efficiency laboratory curiosity into a 14.2% efficiency, cost-declining, commercially certified product wasn't a single discovery moment. It was a company willing to spend a decade doing unglamorous process engineering across 5 different disciplines simultaneously. backed by a home market large enough to make the learning curve affordable. That's a different kind of innovation pipeline than the one most Western energy policy is built around, and it's one that's much harder to replicate with a grant program. The next real test isn't a laboratory result or a pilot program. It's the first large-scale BIPV glass tender awarded outside China. A real commercial building, a real competitive bid, a real contract requiring delivery at specification and at scale. When that contract gets awarded, and to whom, will answer a question the trade press spent years arguing about from the sidelines: whether anyone else has actually closed the gap, or whether the vertical stack China assembled over the last decade is a moat nobody else has started digging out from under. There's also a quieter question sitting underneath all of this, and it has nothing to do with efficiency percentages. Buildings last 50 to 80 years. A curtain wall specified today will still be standing, generating or not generating power, in 2080. Every commercial tower going up right now in Riyadh, in Jakarta, in Austin, in Warsaw, is a decision about which category of building it's going to be for the rest of the century. A passive shell that consumes energy for its entire operating life, or a structure that pays part of its own electricity bill from the day the glass goes in. That decision is being made today, building by building, mostly by people who have never heard the term building integrated photovoltaics, and have no reason to have heard it. The gap between what's technically possible and what's actually getting specified in construction documents this year is where the real story is happening. And it's not a story engineers get to resolve on their own. It belongs to code bodies deciding whether BIPV glass counts as a qualifying energy system. It belongs to developers running payback calculations against 10-year leases. It belongs to insurers who haven't yet figured out how to underwrite a facade that's also an electrical system. And it belongs to governments deciding whether to treat a 15-year manufacturing lead as a supply chain risk worth closing, the way semiconductor policy did, or as somebody else's problem to solve eventually. Both sides of that question carry real weight, and it's worth taking them both seriously rather than picking a winner by default. BIPV glass wins on surface area. Every facade is already committed to going up regardless, so whether it generates power, so the deployment cost is layered onto construction that was happening anyway. Rooftop solar plus storage wins on maturity. The supply chain is global, the installers exist in EVRI market. The cost curve has already collapsed, and it doesn't require rewriting building codes or waiting on a manufacturing stack that currently exists in one country. One path bets on facades becoming infrastructure, the other bets on doubling down on a model that already works and just needs more of it. Where do you land? Is BIPV glass the future of urban energy? Or is rooftop solar plus battery storage still the more practical path for most of the world's cities?